Not a theory, not a guess. A peer-reviewed discovery published in Nature, examined by over 1,000 scientists, and no one can explain what made those patterns except biology. We may have just found proof that life existed on another world. And at the same time, we are building rockets to send human beings to that exact same planet permanently. People whose bones will dissolve in the reduced gravity, whose brains will be slowly rewritten by invisible radiation passing through their skulls every second of every day, who will watch their families grow old in recorded messages that arrive 20 minutes too late to feel real. People who may never come home, not because they chose to stay, because the fuel to bring them back does not exist yet. Tonight, we are going to tell you what it actually costs to go to Mars, not the dream, the price. But before we begin, if you enjoy these nighttime documentaries, remember to like and subscribe. It helps us bring you more videos like this. Now, let's begin. Tonight, we are going to talk about Mars, but not the way you have heard about it before, not the inspirational version, not the billionaire dream, not the shiny rocket on a launch pad with a countdown clock and a crowd cheering in the Texas desert. We are going to talk about what actually happens to a human being who leaves Earth and never comes back. We are going to talk about bones that dissolve, about minds that break in silence, about radiation you cannot see or feel that rewrites the architecture of your brain while you sleep. We are going to talk about a rock on Mars that might contain the fingerprint of something that was once alive, and what it means that we are racing to land on that world before we have finished asking whether we should. We are going to talk about children who may one day be born on another planet, and who will never, for as long as they live, be able to visit the world their parents left behind. And we are going to talk about a company that has already written into its terms of service that no government on Earth has authority over what happens on Mars. This is not a story about exploration. This is a story about exile, and it begins with a delay that almost nobody noticed. Chapter 1. The News They Buried. On February 9th, 2026, while most of America was watching the Super Bowl, Elon Musk posted something on his social media platform that should have made headlines around the world. It did not. There was no press conference, no live stream, no dramatic reveal on a stage with blue lights and a crowd of engineers applauding. Just a few sentences dropped quietly into the noise of a Sunday evening, announcing that SpaceX was shifting its focus away from Mars. The company would now prioritize building what Musk called a self-growing city on the moon. Mars, he said, would have to wait another 5 to 7 years. The overriding priority, he explained, was securing the future of civilization, and the moon was faster. Let that sit for a moment. For over 2 decades, Mars has been the mission, the reason SpaceX exists, the reason Starship was built. The reason Musk told audiences at the International Astronautical Congress back in 2016 that humans would be walking on Mars by 2024, that was the promise, that was the timeline. And every few years, when the timeline slipped, a new one replaced it. 2024 became 2026. 2026 became 2028. And now, in 2026, the target has drifted again. 5 to 7 more years, maybe, if things go well. If orbital refueling works, if the engines hold, if the math cooperates. The pattern is worth examining because it reveals something important, not about Musk specifically, but about the gap between what Mars colonization looks like in presentations and what it looks like in physics. In 2020, Musk said he was highly confident SpaceX would land humans on Mars by 2026. In May of 2025, he said there was a 50-50 chance of sending an uncrewed Starship to Mars by late 2026. By December of 2025, he called the 2026 Mars window a distraction. And by February of 2026, the mission was officially shelved. Every version of the future arrives later than promised, and the reason is not incompetence. The reason is that Mars does not care about timelines. Mars does not care about ambition, or funding, or willpower. Mars is 55 million kilometers away at its closest, and nearly 400 million at its farthest. The physics of getting there, surviving there, and coming back has not changed since the first engineer sketched a trajectory on a whiteboard. What has changed is our understanding of how hard it actually is. But while the world was focused on rockets and launch windows, something else happened, something quieter, something that may turn out to be more important than any rocket ever built. On September 10th, 2025, NASA held a press conference. The acting NASA administrator stood at a podium and said words that scientists have been waiting decades to hear. "A rock on Mars," he said, "may contain the clearest sign of life that we have ever found." The rock is called Chayava Falls. It sits in a place called the Bright Angel Formation, along the edges of an ancient river valley called Neretva Vallis, inside Jezero Crater. The Perseverance rover found it in July of 2024 and drilled a core sample from its surface. What the instruments detected was extraordinary. The rock is made of clay and silt, the kind of fine-grained sediment that on Earth is one of the best preservers of ancient microbial life. Embedded in that sediment were organic carbon compounds, sulfur, phosphorus, and iron, and scattered across the surface were strange markings. Small dark spots the science team nicknamed poppy seeds, and larger formations lighter in the center with dark borders that they called leopard spots. On Earth, those leopard spot patterns are produced almost exclusively by one thing: microbes. Living organisms that consume organic matter and leave behind chemical signatures in the minerals around them. The peer-reviewed paper, published in the journal Nature, examined every known non-biological explanation for how those patterns could have formed. High-temperature processes, chemical reactions without life, geological accidents, none of them fit. The conditions required for those alternative explanations simply do not match the evidence preserved in the rock. This is not confirmation of life on Mars. Scientists are careful with that word, and they should be. But it is the most serious candidate for a biosignature ever found on another world. And the lead author of the study, Joel Hurowitz of Stony Brook University, said something that deserves to be heard clearly. He said that the combination of chemical compounds found in the Bright Angel Formation could have been a rich source of energy for microbial metabolisms, that the organic matter in the mud had reacted with iron and sulfur to produce minerals and textures that, on Earth, are the calling card of living things. And then, just weeks earlier, in August of 2025, another study landed. This one from researchers at New York University, Abu Dhabi, published in the International Journal of Astrobiology. It introduced a concept called the radiolytic habitable zone. The idea is startling in its simplicity. Cosmic rays, the same high-energy particles that threaten the health of astronauts, can penetrate the surface of Mars and split apart water molecules buried underground. When those molecules break apart, they release electrons. And on Earth, there are bacteria that survive by harvesting exactly those electrons. Organisms living deep beneath the surface of our own planet, in total darkness, powered not by the sun but by radiation. The researchers concluded that Mars may have environments, just meters below the surface, where this same process could sustain life right now, not billions of years ago, now. And this is where the story splits into two paths that cannot easily coexist. On one path, humanity is preparing to send people to Mars, to build habitats, to plant flags, to establish a permanent presence on a world that has been lifeless in our imagination for as long as we have been looking at it. On the other path, science is telling us that Mars may not be lifeless at all, that there may be something down there, beneath the red dust, in the frozen water, in the ancient riverbeds, something we have never encountered before, something that would change our understanding of life in the universe forever. If colonists land on Mars and contaminate the surface with Earth microbes before we have confirmed whether Martian life still exists underground, we may destroy the most important scientific discovery in human history. And we may never even know we did it. Earth bacteria are resilient. They hitchhike on everything. On suits, on boots, on the seals of airlocks, on the surfaces of tools. No sterilization protocol is perfect. No habitat is perfectly sealed. The moment a human being sets foot on Mars, Earth life arrives with them. And if Martian life is fragile, if it exists in small pockets sustained by the thin chemistry of radiolysis, it could be overwhelmed and erased by the biological invasion we bring with us. The planetary protection protocols that govern space missions today were designed for robots. for rovers and landers that can be baked in ovens and sealed in clean rooms. They were never designed for human beings, who breathe and sweat and shed skin cells and carry trillions of microorganisms in every square centimeter of their bodies. There is no version of human Mars colonization that does not contaminate Mars. The question is whether that contamination happens before or after we have answered the most profound question science has ever asked. Are we alone? We are racing to colonize a world we do not yet understand. And the window to understand it may close the moment the first human steps off the landing ramp and presses a boot into Martian soil. But the journey to that moment, the actual physical act of getting a human body from Earth to Mars, is a story of distances and durations that most people have never truly reckoned with. We talk about going to Mars the way we talk about flying to another country, as though it is a matter of buying a ticket and enduring a long flight. It is not. The distance between Earth and Mars is not just large, it is a kind of large that changes the meaning of basic human experiences. Communication, emergency response, the ability to say goodbye, the ability to come home. And that distance, measured not just in kilometers but in time and fuel and orbital mechanics, is where the real story of Mars colonization begins. Because once you understand the distance, you begin to understand something that the brochures and the presentations and the inspirational videos never quite say out loud. Going to Mars is not a round trip. Not yet, and maybe not ever. Chapter 2. The distance that eats everything. Imagine you are standing in a room. On one wall there is a light switch. You flip the switch and the light comes on instantly, or at least it seems instant. In reality, the electrical signal traveled through the wire at close to the speed of light, and the delay was so small that your brain could not detect it. Now imagine, the wire is longer, much longer. Imagine it stretches from your wall, out through your roof, past the atmosphere, past the moon, past everything you have ever known, all the way to Mars. You flip the switch, and you wait. 4 minutes, 8 minutes, maybe 20, depending on where Mars is in its orbit. The signal, traveling at the fastest speed anything in the universe can travel, takes between 4 and 24 minutes just to arrive. That is the speed of light, the absolute cosmic speed limit. Nothing moves faster, not radio waves, not laser beams, not the desperate voice of a mission controller shouting instructions into a microphone. And it means that communication with Mars is not a conversation, it is correspondence. Every message sent from Earth arrives minutes after it was spoken. Every reply takes minutes more. A simple exchange of question and answer can take 40 minutes or longer. Now imagine an emergency. A pressure seal in the habitat fails. The atmospheric alarm triggers. An astronaut has seconds, maybe a minute, to identify the breach and begin emergency procedures. They call Earth. They describe what is happening. Their voice, traveling at the speed of light, takes 14 minutes to reach mission control. The engineers on Earth hear the message, process it, formulate a response, and send it back. Another 14 minutes. 28 minutes have passed since the astronaut called for help. In 28 minutes, the astronaut is either alive because they solved the problem themselves, or they are dead because they could not. Earth did not help. Earth could not help. Earth could only listen, minutes too late, to the sound of someone who may already be gone. This is not a hypothetical designed to frighten you. This is the operational reality of every crewed Mars mission ever proposed. The speed of light is not a technical limitation that engineers can overcome with better antennas or faster computers. It is a law of physics, as immovable as gravity, and it means that the moment a spacecraft leaves the vicinity of Earth, the crew is functionally alone. They can send messages home. They can receive messages from home, but they cannot have a conversation in any meaningful sense of the word, and they absolutely cannot receive help that arrives in time to matter. The distance itself shifts constantly. Earth and Mars are both orbiting the Sun, but at different speeds and different distances. Sometimes they are relatively close. At what astronomers call opposition, Mars and Earth can be as near as 55 million kilometers apart. That is the best-case scenario, the shortest possible distance between the two worlds, and even at that closest approach, a beam of light takes over 3 minutes to cross the gap. But opposition does not last. The planets keep moving. and at their farthest separation, when the Sun sits directly between them, Mars and Earth are nearly 400 million kilometers apart. At that distance, a light signal takes over 20 minutes to arrive, and a round-trip message takes more than 40. For most of a Mars mission, the distance will be somewhere between those extremes, long enough that real-time communication is impossible, long enough that every decision, every crisis, every moment of doubt or fear must be resolved locally by the people on Mars, with whatever resources and knowledge they brought with them. But distance is only half of the trap. The other half is time. Earth and Mars do not align for efficient travel on demand. The geometry of the solar system creates narrow windows, roughly every 26 months, when the two planets are positioned favorably enough to allow a spacecraft to make the crossing with a reasonable amount of fuel. Miss that window, and you do not get to try again for over 2 years. This is not a scheduling inconvenience. This is a prison sentence measured in orbital mechanics. Think about what 26 months means in human terms. It is long enough for a child to go from birth to walking and talking, long enough for a marriage to collapse, long enough for a parent to develop a terminal illness and die before the next window opens, long enough for political regimes to change, for technologies to advance, for the world the astronaut left behind to become a place they no longer fully recognize. The transit itself takes between 6 and 9 months, depending on the trajectory. Add the mandatory surface time, which in most mission architectures is determined not by science goals, but by orbital mechanics, because the crew has to wait for the planets to realign before they can even attempt a return. For a conjunction-class mission, that surface stay is roughly 500 days. 500 days on Mars, not because the mission requires it, but because the universe demands it. Add it all up. 6 to 9 months of transit to Mars, 500 days on the surface, 6 to 9 months of transit back. The shortest plausible round trip to Mars takes approximately 3 years. 3 years, not 3 weeks, not 3 months. 3 years of a human life spent inside sealed vessels, exposed to radiation, separated from everyone they have ever known by a communication delay that makes real human connection impossible. And that is the optimistic scenario. That is the version where everything works perfectly, where the return vehicle is fueled and functional, where the launch window is met, where no equipment fails and no crew member becomes too sick to travel. The pessimistic scenario, the one that mission planners discuss in quieter rooms, is that the return simply does not happen, that the technology required to bring people home from Mars does not work as planned, and the 3-year round trip becomes a permanent stay. But we will get to the fuel problem later. For now, consider the decision itself. There is a moment, early in the journey from Earth to Mars, when a spacecraft crosses a line that has no physical marker, but that changes everything. It is the point of no return, not a place in space, but a calculation. The point at which turning around and coming back to Earth requires more fuel than continuing forward to Mars. Within weeks of departure, sometimes within days, an abort becomes harder than completion. The crew is committed, not by choice in any ongoing sense, but by physics. They chose to go when they boarded the spacecraft. Every moment after that, the universe is making the choice for them. Think about what that means for the psychology of the mission. Every other dangerous expedition in human history has had some version of a way back. Shackleton, trapped in Antarctic ice, could still attempt to reach land. The crew of Apollo 13, hurtling past the moon with a crippled spacecraft, had Houston talking them through every second of the crisis, with a response time measured in seconds, not minutes. Submarines can surface, mountain climbers can descend, even sailors lost at sea can drift toward shore. A Mars crew has none of these options. There is no shore to drift toward. There is no surface to reach. There is only forward, toward a planet that is trying to kill them in ways we have not even finished cataloguing, or backward, toward an Earth that is already too far away to help. The historical comparisons that people like to draw, the Mayflower, the Polynesian navigators, the first expeditions to the Antarctic, all share one crucial feature that Mars colonization does not. In every one of those cases, the environment being traversed, however dangerous, was made of the same air and water and gravity that the human body was designed for. A sailor lost in the Pacific could breathe. A settler on the American frontier could drink from a river. An Antarctic explorer could step outside and, however cold it was, the atmosphere would not boil the fluid from their lungs. Mars offers none of these mercies. The space between Earth and Mars is a vacuum that will kill you in seconds. The surface of Mars is an environment so hostile that unprotected exposure causes death within minutes. And the distance that separates the two worlds is so vast that no rescue mission currently conceivable could reach a stranded crew before their supplies ran out. This is the architecture of the journey, not a voyage, but a commitment, not an expedition, but an exile. The distance does not just separate you from Earth. It separates you from every safety net that human civilization has ever constructed. Every hospital, every fire station, every friend who could come and hold your hand, every system designed to catch you when you fall. On Mars, when you fall alone, and the people who love you find out about it 20 minutes later. The engineers designing these missions know all of this. They have calculated every trajectory, every fuel requirement, every communication delay, down to the millisecond. They have built redundancy into systems and trained crews for every conceivable emergency. And still, when you ask them in private whether the return journey is guaranteed, the honest ones pause before answering. Because they know that the return depends on a chain of technologies and conditions that has never been tested, end to end. That the plan to come home from Mars is, at this moment, still partly theoretical. And if the return does not work, then the 26-month window becomes not a scheduling constraint, but a clock counting down to the next chance that will never come. And the distance, which was supposed to be temporary, becomes permanent. The 55 million kilometers between you and everyone you have ever loved becomes a wall that no amount of wanting can bring down. Is a plan that cannot be aborted actually a plan? Or is it a promise made to people who are not in a position to refuse? That question haunts every mission architect who has ever sketched a trajectory to Mars. And it should haunt the rest of us too, because the people who will fly that trajectory are not abstractions. They are human beings with families and memories and fears. And once they cross that invisible line, the point of no return measured not in kilometers but in commitment, they belong to the distance. And the distance does not give anything back. But the journey is only the beginning, because even if the spacecraft arrives safely, even if the landing succeeds, even if the habitat inflates and the life support hums to life, and the first human being takes a breath of recycled air on the surface of another world, there is still the question of what Mars does to the body that arrived. Not the mind, we will get to that. The body, the bones and muscles and eyes and heart that evolved over millions of years to function in one specific gravitational field on one specific planet. The human body is an extraordinary machine. It adapts, it compensates, it adjusts to whatever conditions it finds itself in, with a faithfulness that would be admirable if it were not, in this case, so cruel. Because the body does not know that you want to go home. It only knows where it is. And on Mars, where it is means gravity that is 38% of what it knew on Earth. And the body, dutifully, begins to change. It begins to become Martian, and it may never be able to change back. Chapter 3. A body that becomes alien. Start with bone, because bone is where the betrayal begins. Your skeleton is not the dead scaffolding it appears to be. It is alive. It is constantly being torn down and rebuilt by two types of cells that work in opposition. Osteoclasts dissolve old bone. Osteoblasts build new bone. In a healthy body under normal gravity, these two processes balance each other. Your skeleton replaces itself completely roughly every 10 years. You are, in a very real sense, not walking on the same bones you had a decade ago. But this balance depends on something your bones take for granted. Gravity, mechanical loading, the constant downward pull that tells your skeleton it needs to remain strong. Every time you stand up, every time you walk across a room, every time you climb a flight of stairs, your bones receive the signal that says, yes, keep building, stay dense, stay hard, you are needed. In microgravity, that signal disappears. The osteoclasts keep working. They dissolve bone on schedule, because that is what they do, but the osteoblasts slow down, because the mechanical signals that drive their activity are gone. The result is a net loss. Bone density drops by 1 to 2% per month in the weight-bearing regions of the skeleton, the hips, the spine, the legs, the parts of you that exist specifically to hold you upright in a gravitational field. A 6-month transit to Mars, spent in the microgravity of a spacecraft, produces a bone density loss of 6 to 12%. That is before you even arrive. That is just the price of the journey. And then you land on Mars, where gravity is 38% of what your body evolved for. Is that enough to stop the loss? Nobody knows. We have never tested it. The International Space Station operates at near zero gravity, and everything we know about bone loss in space comes from that environment. We have no data on what happens to human bones at 0.38 g over months or years. We are guessing. The best guess, based on animal studies and modeling, is that Martian gravity may slow the decline but not stop it. Now add the return transit. Another 6 to 9 months in microgravity. By the time a Mars astronaut arrives back on Earth, assuming they come back at all, they may have lost 20 to 30% of their bone density in the weight-bearing regions of their skeleton. To put that in perspective, a postmenopausal woman with osteoporosis has lost roughly 30% of her peak bone density. A returning Mars astronaut could arrive home with the skeleton of an elderly person, regardless of their actual age. And here is the part that the recovery studies do not advertise loudly enough. Bone loss in space is not fully reversible. NASA astronaut Scott Kelly spent 340 days aboard the International Space Station, the longest continuous stay by an American. After his return, studies showed that while some bone density recovered, the microarchitecture of his bones, the internal structure that gives bone its strength, had been permanently altered. The bone came back, sort of, but it came back different, weaker, more brittle, less capable of withstanding the forces that daily life on Earth demands. Scott Kelly spent less than a year in space. A Mars round trip takes 3. We have no data for what happens at that scale. We are sending people into an experiment that has never been run, using their own bodies as the test subjects. But bone is only the beginning. The skeleton is just the most measurable casualty of a body under siege. The eyes are next. In 2011, NASA identified a condition that would come to be called Spaceflight-Associated Neuro-Ocular Syndrome, or SANS. Roughly 2/3 of long-duration astronauts experience some degree of visual impairment. The mechanism is fluid shift. On Earth, gravity pulls blood and cerebrospinal fluid downward, toward your feet. In microgravity, that fluid redistributes toward your head. The increased intracranial pressure pushes against the back of the eye, distorting the optic nerve, flattening the eyeball, causing changes in vision that range from mild blurriness to significant impairment. Some of these changes reverse when the astronaut returns to Earth. Some do not. Several astronauts have reported permanent changes to their vision after long-duration missions. They came home seeing differently than when they left, not because of an injury, not because of a disease, because their own body, adapting faithfully to the conditions it found itself in, reshaped the organs they see through. Now consider the heart. Your heart is a muscle. Like all muscles, it responds to demand. In Earth gravity, your heart works constantly to pump blood upward against gravity, to your brain, to your arms, to every part of you that sits above your center of mass. In microgravity, that work is no longer necessary. Blood flows freely without the need for the heart to pump against a gravitational gradient. And so the heart does what any muscle does when its workload decreases. It atrophies. It gets smaller. It gets weaker. When an astronaut returns to Earth after a long-duration mission, their heart must suddenly resume pumping against full gravity with a muscle that has been downsized for the job. The result is orthostatic intolerance. The inability to stand without fainting. Blood pools in the legs. The weakened heart cannot push it back up to the brain fast enough. The astronaut stands, feels dizzy, and collapses. This happens to almost every astronaut who returns from long stays in space. It is documented, expected, and planned for. Medical teams are waiting when they land. On Mars, there will be no medical team waiting. The crew arrives after 6 to 9 months in microgravity and must immediately begin functioning in a gravitational field. Reduced gravity, yes, but gravity nonetheless. If their hearts have atrophied during the transit, if their cardiovascular systems have remodeled for 0 G, the simple act of standing up and walking across the surface of Mars could be a medical event. And then there is the spine. In microgravity, without the compressive force of gravity, the intervertebral discs expand. Astronauts gain 1 to 2 inches in height during space missions. This sounds harmless. It is not. The expanded discs are more vulnerable to herniation. Back pain is nearly universal among returning astronauts. And herniated discs, which can cause severe pain, numbness, and loss of mobility, are documented at elevated rates in the years following spaceflight. Each of these systems, bone, eyes, heart, spine, fails in its own way. But together, they create something worse than any individual degradation. They create a cascade. A body that has adapted, faithfully and irreversibly, to a place that is not home. A body that has become optimized for reduced gravity, for fluid distributions that do not exist on Earth, for a cardiovascular workload that Earth does not offer. The cruelty is in the faithfulness. Your body does not resist the changes. It embraces them. It is trying to help you survive where you are. It does not know that you want to go back. And this brings us to a question that no one can yet answer, but that should keep every mission planner awake at night. If a colony on Mars survives long enough, if the habitats hold and the life support functions, and the food production works, and the radiation does not kill everyone first, then eventually there will be children born on Mars. Not astronauts who chose to go, not volunteers who signed consent forms. Children, human beings who had no say in the matter. A child born on Mars will develop in 38% gravity from the moment of conception. Their bones will form under a gravitational load that is less than half of what human skeletons evolved to support. Their muscles will calibrate to Martian conditions. Their cardiovascular system will develop for a world where pumping blood is easier, where the heart does not need to be as strong, where the entire architecture of the circulatory system can afford to be smaller, thinner, less robust. Animal studies in simulated partial gravity suggest that developing organisms in sub-Earth gravity produce skeletons and musculature insufficient for terrestrial conditions. Bones that formed under reduced gravity lack the density and microstructure needed to withstand normal Earth gravity. Muscles that developed without full gravitational loading cannot generate the force required to move a body that suddenly weighs 2.5 times what it has ever weighed before. A child born and raised on Mars may be biologically incapable of ever visiting Earth. Not because of a travel restriction, not because of politics or cost, because their body, the body that Mars built, would collapse under the weight of the world their parents came from. Their bones might fracture, their heart might fail, their spine, calibrated for a gentler gravity, might compress in ways that cause permanent damage. We have never run this experiment with humans. We have no data. We have models, extrapolations, educated guesses. But we do not know, with certainty, what happens when a human being develops from embryo to adult in 38% gravity. What we do know is that gravity shapes everything about how a body is built. And if that gravity is wrong, if it is too little, the body that results will be calibrated for a world that is not Earth. The first generation born on Mars would not be colonists. They would be exiles. Trapped not by choice but by biology on a world they did not choose, unable to visit the planet. That every story and every screen and every voice from Earth tells them is home. Home, for them, would be a concept, a word attached to a pale blue dot in the sky that they can see but never touch. Their parents chose Mars. The children inherited it, and the distance between those two experiences, the distance between choosing exile and being born into it, may be the most profound ethical question that Mars colonization forces us to confront. But the body does not only have to contend with gravity. There is something else in the journey between Earth and Mars, and on the Martian surface itself, that is invisible, silent, and relentless. Something that passes through the walls of spacecraft and the fabric of spacesuits and the tissue of the human body without slowing down. Something that rewrites DNA, disrupts neural connections, and increases the probability of cancer with every second of exposure. It is radiation, and it is, in many ways, the most terrifying threat of all, because you cannot see it, you cannot feel it, you cannot run from it. And on the way to Mars, and on the surface of Mars, there is nowhere to hide. Chapter 4. The Invisible Killer. On Earth, you are protected by two shields that you have probably never thought about. The first is the magnetosphere, an invisible bubble of magnetic force generated by the churning iron core deep beneath your feet. It deflects most of the charged particles streaming through space, bending them away from the planet like water around a stone in a river. The second is the atmosphere, a thick blanket of gas roughly 100 kilometers deep that absorbs and scatters whatever radiation the magnetosphere lets through. Together, these two shields reduce your annual radiation exposure to roughly 2 to 3 millisieverts, a dose so low that your body repairs the damage almost as fast as it accumulates. On Mars, both shields are gone. Mars lost its global magnetic field billions of years ago, when its iron core cooled and solidified. Without that magnetic dynamo, there is nothing to deflect the charged particles that fill interplanetary space. And the Martian atmosphere, what remains of it, is less than 1% of Earth's atmospheric pressure, too thin to block cosmic radiation, too thin to stop the high-energy particles that have been traveling through the galaxy for millions of years at nearly the speed of light. The radiation environment between Earth and Mars, and on the Martian surface, consists of two distinct threats. Understanding both of them is essential to understanding what a Mars mission actually does to the people inside it. The first threat is solar particle events. These are bursts of radiation ejected by the Sun during solar flares and coronal mass ejections. They are violent, intense, and somewhat predictable. When a major solar event occurs, a storm of protons and electrons races outward through the solar system at speeds approaching a significant fraction of the speed of light. If a spacecraft or a surface crew is caught in the path of one of these storms without adequate shielding, the radiation dose can be severe, high enough to cause acute radiation sickness, high enough, in extreme cases, to be fatal. The good news, if you can call it that, is that solar particle events can be partially shielded against. The protons they contain are relatively low in energy compared to the other type of space radiation, and a few centimeters of water, polyethylene, or even regolith piled over a habitat can reduce the dose substantially. The bad news is that you need warning. You need time to get inside a shielded area. And on the surface of Mars, with no magnetic field and almost no atmosphere, the warning time for a solar particle event could be as little as 15 minutes. The second threat is far worse, and it is the one that keeps radiation biologists awake at night. Galactic cosmic rays. These are not particles from the Sun. They are the remnants of supernovae, the explosions of dying stars that occurred millions or even billions of years ago in other parts of the galaxy. The nuclei of atoms, stripped of their electrons, accelerated to nearly the speed of light by the unimaginable forces of stellar death. They have been traveling through the cosmos for eons, and they carry energies so high that no practical amount of shielding can stop them. This is the part that defies intuition. You might think that thicker walls would solve the problem. More metal, more protection, more stuff between you and the radiation. But galactic cosmic rays do not behave like ordinary radiation. When a high-energy cosmic ray nucleus strikes a sheet of aluminum, it does not simply stop, it shatters. It breaks apart into a spray of secondary particles, neutrons, protons, pions, gamma rays that scatter in all directions. These secondary particles can actually deliver more biological damage than the original cosmic ray would have on its own. This is called the secondary particle cascade, and it means that thin shielding can make the radiation problem worse, not better. Adding a few centimeters of aluminum to a spacecraft hull can increase the total biological dose the crew receives, because the secondary particles generated by the shielding are more damaging to human tissue than the primary cosmic rays passing through. The Curiosity rover carried a radiation detector called RAD during its transit to Mars in 2011 and 2012. It measured an average dose rate of roughly 1.8 millisieverts per day in deep space. Let that number settle. On Earth, you receive 2 to 3 millisieverts per year. In deep space, you receive that amount every day and a half. A 6-month transit to Mars accumulates approximately 300 millisieverts. The surface of Mars, with its thin atmosphere providing minimal shielding, adds another 0.67 millisieverts per day. A 500-day surface stay adds roughly 335 millisieverts more. Add the return transit, and a complete round trip to Mars exposes the crew to somewhere between 600 and 1,000 millisieverts of radiation. For context, NASA sets career exposure limits for astronauts that are designed to keep their excess lifetime cancer risk below 3%. A Mars round trip approaches or exceeds those limits. And NASA's own peer-reviewed studies have estimated that the radiation-induced mortality risk for a Mars mission crew could exceed 5%, with upper bounds approaching 10%. 10%. 1 in 10. That is not a risk statistic for an experimental program. That is a mortality rate that would shut down any commercial airline, any hospital, any industrial operation on Earth. And it accounts only for cancer. It does not include the other thing that radiation does, the thing that may be more frightening than cancer because it is more immediate and harder to detect. It damages the brain. Researchers at the University of California, Irvine have conducted some of the most detailed studies ever performed on the effects of cosmic ray analogues on the mammalian nervous system. The experiments used particle accelerators to simulate the type of radiation astronauts would encounter in deep space, exposing mice to low doses of heavy ion radiation over extended periods. The results were deeply unsettling. The irradiated mice showed persistent impairments in hippocampal function, the brain region responsible for forming new memories and for spatial navigation. They showed deficits in cortical reasoning, the higher-order thinking that governs problem-solving and decision-making. They showed reduced ability to extinguish conditioned fear responses, meaning they remained anxious and reactive to stimuli long after the stimuli had stopped being relevant. Their dendritic complexity, the branching structures of neurons that form the physical basis of thought and memory, was measurably reduced. The connections between neurons were degraded. In some cases, they appeared to be broken entirely. And these changes were not temporary. They persisted for months after irradiation. In a mouse, months represents a significant fraction of its lifespan. Scaled to a human Mars mission, the equivalent exposure would last not months, but years. The researchers estimated that in a crew of 5 astronauts traveling to Mars and back, at least one member would be expected to display severe cognitive deficits by the time they returned to Earth. At least one. That is not a fringe prediction from an alarmist study. That is a calculation published by NASA-funded radiation biologists based on the best animal data available. Picture what this means operationally. A crew member 18 months into a Mars mission, living inside a sealed habitat on a world where every decision could be the difference between survival and death, is making those decisions with a brain that has been physically altered by invisible particles passing through their skull every second of every day. Their memory may be impaired. Their reasoning may be slower. Their ability to manage stress and fear may be compromised, and they may not notice the decline. That is perhaps the cruelest part. Cognitive degradation is not like a broken arm. You do not feel it happen. You do not look down and see the damage. You simply become slightly less capable, slightly less sharp, slightly less yourself, and you have no way of knowing how much you have lost. The emergency that requires the fastest thinking finds the brain least capable of providing it. And then there are the children. If a colony establishes itself on Mars, if human beings reproduce there, the children born on that world will begin accumulating radiation exposure from the moment they are conceived. Not as adults whose bodies have finished developing, not as astronauts who accepted the risk with full knowledge, as embryos, as infants, as growing children whose cells are dividing faster and more chaotically than at any other period of their lives. Developing organisms are far more vulnerable to ionizing radiation than adults. A cell that is dividing is a cell whose DNA is unwound, exposed, and vulnerable. A mutation introduced during embryonic development can cascade through trillions of subsequent cell divisions, affecting every tissue the mutated cell contributes to. The radiation doses on the Martian surface, accumulated over a childhood, would be unlike anything ever experienced by a developing human being in the history of our species. We have ethical frameworks on Earth that prohibit exposing children to these kinds of risks. Institutional review boards, informed consent requirements, protections for vulnerable populations. None of these frameworks currently extend to children born on another planet. There is no regulation, no treaty, no law that addresses the question of what radiation exposure is acceptable for a child who was conceived on Mars and has no option to leave. Who consented for those children? Who bears responsibility for what the radiation does to their developing brains, their growing bones, their dividing cells? The parents who chose to colonize Mars? The company that transported them? The governments that funded the mission? The engineers who designed the habitats? At what point does the desire to build a new civilization become an act of harm against the people who will be born into it? That question has no answer yet, but it hangs over every Mars colonization plan ever drafted, because every plan that includes long-term habitation implicitly includes the possibility of children. And every child born on Mars will live their entire life inside a radiation environment that we would never willingly expose a child to on Earth. The invisible killer does not discriminate. It does not care about ambition or courage or the dream of a multiplanetary species. It passes through walls and skin and bone with equal indifference. And on the surface of Mars, under a sky that offers no protection and no mercy, it will be there every second of every day, doing its quiet, patient work. But radiation is not the only way Mars tries to kill you. The planet itself, its atmosphere, its soil, its weather, is a machine designed for death. And understanding what the surface of Mars actually is, not the way it looks in photographs, but the way it would feel against your skin and inside your lungs, is essential to understanding why going there is not exploration. It is survival, every second, without pause, for as long as you live. Chapter 5. A planet that wants you dead. Mars has an atmosphere. This is important to understand because when people hear the word atmosphere, they picture something like Earth's. A breathable blanket of air, dense and warm, holding in heat and keeping out the void. Mars has nothing like that. What Mars has is a ghost of an atmosphere, a thin wisp of gas pressing down on the surface at roughly 6 millibars. For comparison, the atmospheric pressure at sea level on Earth is 1,013 millibars. The Martian atmosphere is less than 1% of that. This is not just thin. This is functionally a vacuum. If you were to step outside a Mars habitat without a pressure suit, the air inside your lungs would expand violently. The moisture on your tongue and in your eyes would begin to boil, not because of heat, but because of the lack of pressure. At 6 millibars, the boiling point of water drops below human body temperature. Your blood would not boil immediately. Your circulatory system maintains its own internal pressure, but the exposed fluids of your body, your saliva, the tears coating your eyes, the moisture lining your airways, would vaporize. You would not freeze first. The common image of a person stepping onto Mars and turning into an ice sculpture is wrong. You would suffocate. Carbon dioxide, which makes up 96% of the Martian atmosphere, would flood into your lungs with every reflexive gasp. And at concentrations that high, unconsciousness comes within seconds. Death follows within minutes. The temperature adds its own dimension of hostility. The average surface temperature on Mars is negative 60 degrees Celsius. At the equator on a summer afternoon, it can climb to a relatively mild 20 degrees. But at night, at the poles, or during winter, temperatures plunge to negative 140 degrees or below. That is cold enough to freeze carbon dioxide directly out of the atmosphere. Cold enough that the dry ice forming on the Martian surface is not water ice, but frozen gas. A human being exposed to these temperatures without protection would experience rapid core temperature decline. Hypothermia would set in within minutes. Frostbite on exposed skin would begin almost immediately. But again, you would not die of cold. You would die of the atmosphere, or the lack of it, long before the temperature killed you. The photographs of Mars are beautiful. They really are. The russet dunes, the layered canyon walls of Valles Marineris, the soft pink sky at sunset. There is a haunting majesty to the Martian landscape that speaks to something deep in the human imagination. But every one of those photographs was taken by a machine that does not need to breathe, a machine that does not have lungs or blood or skin. The beauty of Mars is the beauty of a place that will kill you the moment your technology fails. And then there is the dust. Mars is a dusty world. Windstorms lift fine particles from the surface and carry them across the planet, sometimes growing into global events that shroud the entire world in a haze that can last for months. The dust itself is remarkably fine, with particles measured in micrometers, far smaller than grains of sand, closer in size to the particles in cigarette smoke, and it is everywhere. It coats every surface. It infiltrates every seal. It works its way into machinery, into joints, into the mechanisms of solar panels and the threads of screws. In 2018, a global dust storm on Mars killed the Opportunity rover. Opportunity had operated for over 14 years, far exceeding its 90-day design life, surviving everything Mars could throw at it. Until the dust came. The storm reduced sunlight reaching the solar panels to near zero for weeks. Without power, the rover's heaters could not function. Without heat, the electronics froze. After 14 years of faithful operation, Opportunity's last transmission was a poetic final data point. Its battery was dying, the sun was disappearing, and there was nothing anyone could do. For a human colony dependent on solar power, a global dust storm is an existential threat. Energy generation drops below the threshold for life support, oxygen production slows, heating systems falter, and the storm does not care about your timeline or your reserves. It can last 100 days. It can last longer. And while it rages, you sit inside your habitat, watching the power gauge decline, rationing every watt, wondering whether the sun will come back before the batteries die. But the most insidious danger in the Martian dust is not what it does to machines. It is what it does to lungs. In 2008, NASA's Phoenix lander confirmed something that changed the calculus of Mars surface operations forever. The Martian soil contains perchlorates, reactive chlorine compounds that are toxic to the human thyroid gland. Subsequent missions confirmed that perchlorates are not localized. They are spread across the entire Martian surface at concentrations that would classify any comparable site on Earth as a hazardous waste area. Perchlorates are colorless, odorless. You cannot see them on the dust that coats your gloves when you come back inside. You cannot smell them on the particles that settle on the surfaces of your habitat. They enter through every pathway available, on the soles of boots, on the fabric of suits, on equipment brought inside for maintenance. They contaminate food production systems. They accumulate in air filtration units. And they do their damage slowly, disrupting thyroid function, interfering with iodine uptake, potentially leading to hypothyroidism and developmental problems over time. And perchlorates are not the only hazard in the dust. Martian soil also contains fine silicate particles that some researchers have compared to the properties of asbestos. These particles, when inhaled, can embed themselves deep in lung tissue, triggering inflammatory responses that may lead to scarring, fibrosis, and eventually cancer. Studies have warned that prolonged inhalation of Martian dust could produce lung conditions similar to those suffered by asbestos workers on Earth, a group whose disease rates are well documented and deeply troubling. The colonist who survives radiation, who survives the transit, who survives the cold and the vacuum and the isolation, may still develop cancer from the dust they could not help breathing. Because you cannot keep dust out of a habitat on Mars. Not perfectly, not forever. Airlocks are designed to minimize contamination, but every time a door opens, every time a suit is removed, every time equipment is brought inside, some dust comes with it. Over months and years, that accumulation adds up. And the particles do not leave your lungs once they arrive. Apollo astronauts on the Moon experienced something similar. Lunar dust, tracked into the command module after moonwalks, irritated eyes and airways. Harrison Schmitt, the geologist astronaut of Apollo 17, described symptoms resembling hay fever after exposure to lunar dust in the cabin, and the Apollo missions lasted only a few days. Mars colonists would be breathing trace amounts of Martian dust for years. For lifetimes. The planet is not just inhospitable, it is actively working against you at every scale. From the global dust storms that can darken the sky for months, to the microscopic particles that lodge in the tissue of your lungs. The atmosphere will suffocate you, the temperature will freeze you, the soil will poison you, and there is nowhere on the entire surface of Mars, not a single square meter, where a human being can stand unprotected and survive. Every second of human life on Mars will depend on technology, on seals that do not fail, on power systems that do not die, on filtration that does not clog, on suits that do not tear, on 1,000 systems working perfectly, simultaneously, without interruption, for years on end. There is no margin for error on Mars because there is no backup. On Earth, if your house loses power, you go to a neighbor. If your car breaks down, you call someone. If the air quality is bad, you go indoors. On Mars, indoors is the only place you can be. And if indoors fails, outside is not an alternative. Outside is death. The engineers designing Mars habitats understand this. They design for redundancy. They build in backup systems and emergency protocols and fail-safe mechanisms. But they also understand something that they rarely say out loud. No system is perfectly reliable over infinite time. Everything fails eventually. Seals degrade, filters saturate, electronics corrode. And on a planet where a single catastrophic failure can kill everyone in the habitat, the question is not whether something will go wrong. The question is when, and whether anyone will be alive to fix it. Mars is not a frontier waiting to be settled. It is an environment that has been lifeless on its surface for billions of years, for very good reasons. And every one of those reasons applies equally to the human beings who propose to live there. But if the planet attacks the body, what does it do to the mind? What happens to a human being who knows, with absolute certainty, that they are trapped on a hostile world, that the people they love are 20 minutes away by light speed, that the door they came through may never open again to let them go home, is less than #0. 5 is greater than. The answer is something that no simulation has fully captured and no training can fully prepare anyone for. Because the psychology of permanent exile is not an engineering problem. It is a human one. And the human mind, for all its resilience, has limits that Mars will test in ways we have barely begun to understand. Chapter 6. The Mind That Breaks. There is a moment in every long isolation that researchers call the third quarter phenomenon. It occurs roughly 3/4 of the way through a confined mission, when the end is close enough to feel, but far enough away to crush morale. In Antarctic winter overstations, the third quarter brings spikes in depression, hostility, and sleep disturbance. In submarine crews, it brings irritability and withdrawal. In space station missions, it brings a measurable decline in communication with mission control as crews begin to pull inward, to stop reporting their emotional states, to manage their suffering in silence. On a Mars mission, the third quarter does not arrive and pass. On a one-way mission, it never ends. The psychological profile of Mars isolation has no true analogue in human experience. We can compare it to other forms of confinement, and researchers have tried. But every comparison eventually breaks down, because every comparison has an escape valve that Mars does not. Astronauts on the International Space Station are isolated, yes, but they can see Earth through the window. A blue sphere that fills the sky, close enough to feel tangible, real, within reach. They can video call their families with delays measured in seconds. They know that if something goes genuinely wrong, if a medical emergency occurs that the crew cannot handle, a Soyuz capsule can return them to Earth within hours. The psychological safety net is enormous. The isolation is real, but it is bounded. It has walls. It has an end date. Antarctic winter over crews at the South Pole endure months of darkness, extreme cold, and near total isolation from the rest of humanity. The nearest help during the winter months is thousands of kilometers away and may not be able to reach them. Depression rates during Antarctic winter are high. Interpersonal conflicts are common. Sleep disorders are nearly universal. And yet, even the most isolated Antarctic crew knows two things. They know it will end. And they know that, in the most extreme emergency, an evacuation flight could be attempted. Risky, dangerous, but possible. Mars colonists have neither of these comforts. They cannot see Earth in any meaningful way. It is a point of light in the sky, indistinguishable from a star. They cannot call home and expect a response in real time. Their messages arrive on Earth minutes after they are sent, and the replies take minutes more to come back. A conversation becomes an exchange of monologues, separated by silences so long that the emotional thread of the interaction breaks. Think about what that does to a relationship. Any relationship. A spouse, a parent, a best friend. Relationships are maintained through spontaneity, through the small, unplanned moments that give human connection its texture, the unexpected call, the shared laugh at something that just happened, the ability to say "I love you" and hear "I love you too" in the same breath. On Mars, none of that is possible. You record a message. You send it into the void. You wait 20 minutes. You receive a response that was recorded 20 minutes ago to something you said 40 minutes ago. The conversation is always out of sync. The emotional moment has always passed by the time the response arrives. Over time, the spontaneity dies. Then, the intimacy follows. Then, the sense of shared time. And eventually, a relationship that was once the center of your emotional life becomes a kind of literary exchange. Letters sent into space. Beautiful, perhaps. Heartfelt, perhaps. But no longer a living connection. Just a record of what was. Children grow up. You watch it in recorded videos that arrive weeks after the moments they captured. A first step, a first word, a first day of school. You see these milestones with a delay that makes them feel like memories before you have even experienced them. Your child is already beyond the moment by the time you learn it happened, and you cannot participate. You cannot cheer. You cannot hold them up. You are a spectator to your own family's life, watching from a distance that no technology can close. In 2010, the Russian Institute for Biomedical Problems conducted an experiment called Mars 500. 6 volunteers entered a sealed facility in Moscow and remained there for 520 days, simulating the duration of a Mars round trip. They had communication delays built into their interactions with the outside world. They had confinement, limited resources, and the monotony of a closed environment. The results were sobering even in that controlled setting. Crew members experienced significant sleep disruption. 2 of the 6 volunteers developed symptoms consistent with depression. Interpersonal dynamics deteriorated over time, with increasing withdrawal and reduced communication between crew members and simulated mission control. The researchers identified a phenomenon they called autonomization, a progressive disengagement from external support structures that mirrors what happens in real, long-duration space missions. And these subjects knew they were on Earth. They knew that beyond the sealed doors of their habitat, Moscow continued to exist. They knew that if a genuine medical emergency occurred, help was literally on the other side of the wall. They knew it would end. Real Mars colonists know none of these things. Every psychological stressor identified in Mars 500 would be amplified by the knowledge that the isolation is real, that the door does not open onto a Russian research facility, but onto a world that will kill you in 90 seconds, and that there is no end date. But there is one dimension of Mars psychology that no simulation has ever tested, one form of suffering that is unique to the condition of permanent exile at interplanetary distance, and it may be the heaviest burden of all: grief. Every Mars colonist will eventually learn that someone they loved has died on Earth. A parent, a sibling, a friend, someone they held once, in a gravity that their body can barely remember. And they will learn this fact not through a phone call, not through a knock on the door, not through the embrace of someone who shares their sorrow. They will learn it from a message, a recorded message that traveled at the speed of light across millions of kilometers and arrived in their inbox hours after the death occurred. They will sit inside a sealed habitat on an alien world and read or hear the words that tell them someone is gone, and they will grieve alone. There will be no funeral to attend, no gathering of people who shared the loss, no ritual, no ceremony, no communal expression of sorrow. Human beings have developed rituals for grief over thousands of years because grief shared is grief that can be survived. The wake, the memorial, the act of gathering with others who knew the person who died and saying together, "This mattered, this person mattered." On Mars, none of that exists. The colonist grieves in a room that smells of recycled air, surrounded by people who have their own losses and their own burdens, on a world that offers no comfort and no release. And the grief does not come once, it comes repeatedly, because everyone the colonist left behind on Earth will continue to age, to change, to eventually die. And the colonist will watch it happen, slowly, across years of recorded messages, watching the people they loved grow older, in a time delay that makes every conversation feel like speaking to a ghost. The anticipation may be worse than the event. The colonist who watches their parent age through recorded videos, who notices the slower movements and the grayer hair and the more careful speech, knows what is coming. They can see the trajectory. And they know that one day, the message will arrive that says it happened, and they will be the last to find out and the only one who cannot come to say goodbye. Can a person remain fully human while grieving alone for years, with no community of shared mourning, no ritual, and no hope of return? That is not a rhetorical question, it is a clinical one. And the answer is that we do not know, because no human being has ever been placed in that condition. We have data on grief in isolation. We have data on grief at a distance. We have data on grief without ritual. But we have no data on all three simultaneously, sustained over years, with no possibility of relief. The psychology of Mars colonization is not an afterthought. It is not a soft problem to be solved with better crew selection, or more exercise equipment, or monthly sessions with a therapist on a 20-minute delay. It is a core engineering constraint, as fundamental as fuel and oxygen and radiation shielding. Because a crew that is physically healthy, but psychologically broken, is a crew that cannot function. And a crew that cannot function, on a world that punishes every mistake with death, is a crew that will not survive. The mind that goes to Mars will be tested in ways that no mind has been tested before. And the question that sits at the center of every psychological study ever conducted on long-duration spaceflight is not whether the mind will break. It is what happens when it does. Because on Mars, there is no evacuation. There is no medical leave. There is no stepping outside for fresh air. There is only the habitat, the red dust beyond the window, and the pale blue dot in the sky that gets a little harder to find with each passing year. And even if the mind holds, even if the body adapts, even if the habitat functions and the crew survives, there is still the question that makes every other question moot. The question of whether they can come home at all, because the technology required to bring a human being back from Mars does not currently exist, and the mathematics of why it does not exist are as unforgiving as the radiation and the distance and the dust. Chapter 7. The fuel that does not exist. There is a law in rocketry that governs everything. It is called the Tsiolkovsky rocket equation, and it was first derived by a Russian schoolteacher in 1897. The equation itself is simple. The implications are brutal. Here is the core problem, stripped of all jargon. To move a spacecraft, you need fuel. Fuel has mass. To carry that mass, you need more fuel. And to carry the fuel that carries the fuel, you need even more fuel. The relationship is not linear, it is exponential. Every additional kilogram of payload you want to deliver to Mars requires not just one additional kilogram of fuel, but many additional kilograms, because each kilogram of fuel added must itself be lifted, which requires its own fuel, which requires its own fuel, and so on. This is sometimes called the tyranny of the rocket equation, and it is not a metaphor. It is a mathematical wall that has defined the limits of space travel since the first rocket left the ground. For getting to Mars, the tyranny is manageable. Barely. A spacecraft can carry enough fuel to make the outbound journey because it does not need to carry the fuel for the return. The mass budget can be spent on payload, on life support, on the 1,000 things a crew needs to survive. But the moment you add a return trip to the equation, the mathematics become catastrophic. To return from Mars, a spacecraft needs fuel. That fuel must be on Mars when the crew is ready to leave. It can get there in one of two ways. It can be carried from Earth, or it can be manufactured on Mars. There is no third option. Carrying return fuel from Earth is essentially impossible with current or near-future technology. The gear ratio is staggering. For every kilogram of propellant you want to deliver to the Martian surface, you must launch approximately 226 kilograms from Earth. That is not a typo. 226 to 1. That ratio accounts for the fuel needed to lift the fuel from Earth's gravity well, to accelerate it to interplanetary speed, to decelerate it at Mars, and to land it safely on the surface. A SpaceX Starship returning from Mars would need somewhere between 33 and 100 tons of methane and liquid oxygen propellant. At a 226 to 1 ratio, delivering even the minimum amount would require launching over 7,000 tons from Earth. For comparison, the Saturn V, the most powerful rocket ever successfully flown before Starship, had a total launch mass of roughly 3,000 tons. You would need the equivalent of more than 2 full Saturn V launches just to deliver enough return fuel for one Starship. The numbers do not work, they have never worked, and they are why every serious Mars mission architecture since the 1990s has relied on the same alternative: make the fuel on Mars. In situ resource utilization, or ISRU, is the name for this idea. The chemistry behind it is real and well understood. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water. Electrolysis splits water into hydrogen and oxygen. Mars has abundant carbon dioxide in its atmosphere and water ice beneath its surface. In principle, a chemical plant on Mars could extract these resources, process them, and produce the methane and liquid oxygen that a Starship needs to fly home. NASA even demonstrated a proof of concept.